So let's get started. Today we are going to start chapter 14. In this chapter, we are going to talk about the principle of work and energy. And in order to understand the principle of work and energy, we need to understand the work of a force. We know that a force does a work on a particle when the particle undergoes a displacement along the line of action of the force. And I think you have background about that in physics. So we learned in the previous chapter, we learned the equation of motion. And also we discussed how to apply the equation of motion. Say first we need to come up with the free body diagram, and then we are going to use the scalar component if you are working with 2D problem. And you need to decompose the forces into X and into Y, and you need to show a free body diagram showing all the external forces, and also you need a kinetic diagram showing the inertial forces. Today we need or we would like to develop another equation to help us to determine the velocity and the displacement and the forces. We know that the equation of motion relate the forces and the acceleration. And in order to determine the velocity and the displacement, we need to use the kinematic equation. Now we need to develop a new equation that can relate the forces with their velocities and their positions. So we are going to start with the equation of motion, this one here. And also from the kinematic equation, we define the acceleration by v, the velocity, times dv over ds. So we can substitute the value of a and put this value here, v dv over ds. Then if we are going to integrate this, we are going to end up with the principle of work and energy. And this principle is useful for solving problems that involve force, velocity, and displacement, like I just mentioned. And also it can be used to explore the concept of the power. But before that, before we are going to integrate this equation after substituting the value of 80 with this expression, we need to understand the work of a force, because this equation is going to involve determining the work acting on the particle. So before we do the integration, we need to understand or review the work of a force. So assume that I have a path like that, and assume the initial position was S1 and the final position is S2. And I have a particle moves along that path. Then we have a force acting on that particle. And as a result, that particles move very small distance, ds, from this point to that point. So we are going to say that a force does a work on a particle. So if that particle moved a distance because of that force, we are going to say that a force does a work on a particle when the particle undergoes a displacement along the line of action of the force. So displacement, it should be along the line of action of that force. Sometimes we have angle between the direction of the displacement and the force. In that case, I need to determine the component of the force along that line. In that case here, the component of the force along the line of the displacement is going to be F cosine theta. And if I multiply the force component along the line of displacement by ds, then I'm going to get the work. I'm going to say that that force does a work on the particle. So if that displacement is very small, ds, then I'll be able to determine the increment of the work. I'm going to determine du. So if the angle between the force and the displacement vector is theta, so the displacement here is theta, then the increment of the work du done by that force is going to be du equal f cosine theta, the component of the force along the displacement, times the small displacement ds. So here is the path s, so this one here is ds. If I want to know the work that done from S1 to S2, then I need to integrate. So I need to integrate for that path from S1 to S2. So the work done between the point 1 and point 2, or position 1 and position 2, is going to be the integration from S1 to S2, f cosine theta times ds. And this is the definition of the work. We have special cases regarding the work. For example, what if that path was straight and the value of the force is constant? So we have a special case here. We are going to assume that the path here is straight line, and that force here is constant, which means that that force is not going to change with the time. The value is constant, whether the particle is here or there. So along that path, the force is constant. The line here is a straight line. In that case, we are going to say that we have a work has been done from position 1 to position 2. So the particle moved from position 1 to position 2. And as a result, we are going to say that that force does a work on the particle. And that work is going to be the f cosine theta, the component of the force along the direction of the displacement, times the difference here between that position and that position, which is S2 minus S1. So if I have case like that, I'll be able to determine the work that has been done on the particle between position 2 and position 1. So in general, if I have a particle and I have a force acting on a particle, and as a result, the particle undergoes displacement along the direction of the force, then we are going to say that a force does a work on the particle. Also, it's very important point here. The work, it could be positive or it could be negative. So the work is positive if the force and the movement are in the same direction. So if here is the direction of the force and the direction of the displacement also in this direction, in that case, the work is positive. If the displacement in this direction and the force in the opposite direction, that means the work is negative. So if the force and the displacement, they are opposing, in that case, the work is negative. And if the force and the displacement direction are perpendicular, then the work is 0. So if the force here was perpendicular, was in this direction, in that case, the value of theta is going to be 90. Okay, which means that the force here is perpendicular to the work. In that case, the work is 0, because if you are going to substitute here, 90 cosine 90 is 0. So if the force is perpendicular to the direction of the displacement, then no work will be done. Also, we know that the particle is going to have a weight. So here you could have a weight with the force. We know that the weight also is a force. So if I have case like that, since the weight is going to be perpendicular, in that case, the work is not going to cause any work. But we are going to talk about general path. So if I'm going to have a path like that, the initial position is S1 and the final position is S2. The particle moved from here to there. Okay, we know that the displacement, the particle, since it moved from here to here, that it means that I have displacement in the y direction. And the difference between y2 and y1 is going to give us the displacement in the y direction. And here we know that the weight is going to act down. So the weight is acting down, and also we have displacement in y. So in this case, also we are going to have a work done by the weight. So we are going to say that the work done from the position 1 to position 2 is going to be minus W, because the weight is going to act down, times y2 minus y1. And the work which has been done by the weight, it could be positive or it could be negative. So if the displacement here, the direction of the displacement is opposite to the direction of the weight, then the work is going to be negative. And here we are going to assume that the general case is going to be negative. We are going to assume that the direction of the weight is going to be opposite to the direction of the displacement. So if delta W, the difference in y, if it's upward, that means the work is going to be negative. So the weight of the work of the weight is a product of the magnitude of the particle's weight and its vertical displacement. Here the particle weight, and here is the displacement. If delta y is upward, if that one was upward, then the work is going to be negative. And if it's downward, in that case, the work is going to be negative. The bottom line here, if the direction of the displacement is in the same direction of the force, then the work is going to be negative. If they are opposing each other, then the work is going to be negative. Also, in many cases, the particle is going to be connected to a spring. So also, the spring will do a work for that particle. In many cases, the particle is going to be connected to a spring. If an elastic spring is elongated along a distance ds, so here I have a particle, and we are going to say that that spring has been elongated to a small distance ds, only this distance here. So the particle was here, it moved a distance ds, which means that the spring has been stretched. Then the work done by the force that acting on the attached particle is going to be du minus fs ds. Here we put minus fs because we know that the force of the spring is going to be opposite to that direction. So if the displacement is here, the spring is going to act opposite to the direction of the displacement. That is why the value of fs should be negative. Now the displacement is very small, only ds. What if I have a displacement from S1 to S2? Assume S1 is here and S2 is there. In that case, I need to integrate. I'm going to integrate from S1 to S2, and the displacement is Fs times ds here, and we know that Fs is going to be negative. And if you do recall from the previous lectures, the forces acting on the spring is K times S, and the minus for the opposite direction. If I'm going to integrate this part here, then the integration, the work done from 1 position 1 to position 2 is going to be minus 1 over 2 ks squared minus 1 over 2 ks1 squared. So in order to determine the work done by spring, I need to know the value of k, the constant of the spring. Also, I need to know the position 2, and I need to know the position 1. You have to remember that the value of S is going to be measured from the unstretched position. Unstretched position, that means the spring, the original length of the spring. So S is going to be measured from here, not from there. It's a common mistake that the student is going to determine the value of S from here. And this is a mistake. You need to determine the value of S from the unstretched length. So here is my reference, not here. So now let's see example so that we can apply what we have learned. We need to determine the work done on that box here because of that applied force and the weight of the block and the spring here. So we have 10 kilogram block. We have a block. The weight of that block is 10 kilograms. And it's resting on a smooth incline. We have incline, and the surface here is smooth. If it's smooth, that means we don't have any friction. They say that if the spring is originally stretched 0.5, so before we apply that load, the spring has its stretch equal 0.5. So here we have stretch by 0.5, which means that here I have the unstretched position. So my reference is here in order to determine the work on the particle because of the spring. Here is the unstretched length. Here is the S1, the initial position. At the initial position, we have stretch equals 0.5. Then the block moved from here to here by a distance equal to meters. So S1 is 0.5 and S2 is going to be 2.5 because my reference is from here. Take care of that point. It's very important. The question is determine the total work done by by all the forces. So we need to determine the total of the work that has been done by the forces here. We have the forces of the spring in this direction. We have the forces of the applied force, and we have the force of the weight. And the value of P here is 400 newtons. It's going to push the block up to the plane where the value of S here is 2. And S equal to from the S equals 0.5. So the displacement is 2 in that case. So we need to determine the work done by all of the forces. So let's start with the horizontal force. Here we have the block, and here we have horizontal force. And the angle here is 30 because the angle here is 30. And also this one here is going to be 30. Because if this one X and Y, and you make rotation, new X and Y, then this angle is going to be 30, and also this angle here is going to be 30. So first we need to determine the work that has been done by the horizontal force P. Remember, we say that the displacement is going to be along that direction here. But the force, like you can see, the force is in that direction, is horizontal. And the displacement along that line. So remember, in order to determine the work, we need to know the component of the force along the displacement. The displacement is here. So we need to know the component of the force along the displacement, the direction of the displacement. So in that case, we need to know the component of the force along that direction. So the component of the force is going to be 400 cosine 30. And it's going to be in this direction, in the same direction of the displacement, which means that the work here is going to be positive. So the displacement times the component of the force in the direction of the displacement. This is a very important point. And in that case, the work done by the force P is going to be 400 cosine 30 times 2 meters, the displacement. So the displacement is like that. So the direction is like that here. And the work is positive because the force and the displacement are in the same direction. Now let's see the weight. We said that the weight also is going to we are going to have a work as a result of the weight as well. And remember, we said that the work done by the weight is going to be minus W times the difference in Y. So in this case here, the block was here, and then the block has been moved there. If this one is 2 meters, that means the distance here is going to be 2 sine 30, and that distance is going to be 2 cosine 30. And the weight is going to act down. So because of the weight, we have vertical displacement, and the weight also is vertical. So in that case, we are going to multiply the weight times the vertical distance. Or I can decompose the weight into X and into Y. And in X here, the component into that direction is going to be along the displacement. So I can multiply 9.81 sine 30 times the 2. And like you can see here, the direction of the weight is opposite to the direction of the displacement. It means that the work done by the weight is going to be negative. Also here, remember, we said that if the delta Y is acting upward. So now delta Y is acting upward, not downward. That means the work is going to be negative. Here I have the dy, here is the dy, and here I have the weight, which is acting down. So the work done by the weight is going to be minus 9.81 sine 30 times 2 meters. Here I have the difference in y. And it's negative because the difference is upward, not downward. Now, also we have the normal force. Remember here, we have a normal force. But the normal force, like you can see, is perpendicular to the direction of the displacement, which means that the normal force will not cause any work. So the force does no work regarding the MB, since it's always perpendicular to the displacement. Whatever the position, the normal force is going to be perpendicular to the displacement. So we are going to say that this force does no work. Then let's go to the spring. We have a spring here. And since the displacement is going to be this direction, the spring is going to be opposite to that one. So the spring is going to be negative. But we need to know the value of S1 and S2. Remember, the reference is going to be at the unstretched position. So at S1, we have stretch by 0.5, and here is going to be 0.5 plus 2. So S1 is 0.5 and S2 is 2.5. Again, take care of that S1 and S2 when you are going to deal with the spring force. Many students make mistake here. You need to remember your reference is here. So we develop this formula. We said that the work done from the S1 to S2 is going to be like that. I need to know the value of K. The value of K is given, which is 30 Newton per meter. And the value of S1 is 0.5, and the value of S2 is 2.5 meters. I'm going to substitute all of this. and the value of the work done by a spring came out to be minus 90. It's minus because the spring is going to apply a force opposite to the direction of the displacement. So now I need to determine the total work that has been done by all the forces. Here I have the value, the work has been done by the horizontal force is positive. Here I have the work has been done by the weight, it's negative. And here I have the work has been done by the spring force, which is negative. Then the total, the work of all the forces when the block is displaced 2 meters is going to be 505 joules. Okay, so now we managed to determine the value of the of the total work. Of course, joule is Newton meter. I'm going to stop here. I'm going to give you the chance in order to ask questions